Here we go. Now we have some volume. Excellent. So let's start the class. All right. Shall we begin? Let's hit the mood lighting. Better? Better? Worse? Worse? Better? Better. Okay. Who doesn't like this? All right. So let's hit. How about this version? No, it's not good still. That's probably the best we can do. Hi, everybody. Ah, jeez. I've been teaching since 8 a.m. So this is non-stop classes. This is great. How was the labs? Was that useful? Any problems with the labs this week? It was just basic recipe stuff, following the opening SPSS and doing some fun stuff. Okay. Like I said, if you have any particular requests to doing stuff in the labs, let me know. We can modify the assignments. But the goal is to get you some experience running SPSS and just getting comfortable with the idea of using high-powered SAS software. And maybe, if we're curious, I can introduce some more complicated software later in the semester, if there's interest. So, last week we started this bivariate analysis stuff. And remember, bivariate means two variables. And we started the process of looking at ways of measuring relationships between variables. And we looked solely at two dichotomous variables, right? So risks and exposures in this case, odds ratios and relative risks. Today, we're going to move on to two different kinds of variables. So continuous variables or ordinal variables, right? And obviously, I'm alluding to the idea of correlation. And it'll be probably a quick lecture. It'll get you out fast if things go smoothly. And we're online, we're live, things are going well. I'm surprised. Hey, so far the technical aspects are working well. Knock on fake wood. So you can see me, right? Have we started the assignment? Excellent. You can use the lab time to help work on that as well. I don't mind if you do it by hand or use a computer. For this particular assignment, I just care about the answers. And the second assignment will be more about the details. All right? So a bit of recap from last time. We talked about the relative risk being the best estimate of a relationship between an exposure and an outcome, or an independent variable and a dependent variable in a public health context. We also talked about the odds ratio, but the odds ratio is just an estimator of the relative risk, because a relative risk has no meaning in a case control method. Remember, a case control method is when I select my cases, the people who have the disease or the outcome, and people who don't have the disease, which are the controls, and I look backwards in time to see which group had what exposure. So by looking backwards in time, I can't do risk, I can't do incidence, therefore I can't do relative risk. So instead I compute an odds ratio, which is meant to estimate a relative risk, right? Excellent. Now remember, I can compute a relative risk, but it won't mean anything. I can do the math, but it won't mean anything. That's why an odds ratio is important. Now, a couple of notes on relative versus absolute measures. Anytime we have something divided by something else, a ratio, a rate, something per something, that's a relative measure. Anytime I just give you a number, like the number of people in this class, the percentage of women in this class, that's an absolute number. So the number of children you have, the number of infected cases in my sample, the temperature in this room, the average age in my sample, these are absolutes. Relative is the number of cases per 1,000 people, number of children per family, that kind of thing. Why is this important? Because you can tell the wrong story if you choose the wrong kind of measurement. So here is from 1994-95, the prevalence of a dumbass disease in Loserville increased by 300%. Oh my God, 300%, that's huge. However, the absolute numbers went from 1 case to 4 cases. That's a 300% increase. So depending upon which story you tell, you get a different implication. And this is obviously a fake example, but a few years ago in Ontario, I think the number of cases of cholera doubled, and the media went crazy. The case of cholera doubled. It went from 2 cases to 4 cases. Right? It wasn't that big a deal. So the actual number of cases is an absolute measure, and something per something is a relative measure. The one that you choose depends upon the story you're trying to tell. Okay, so a relative measure can be misleading, so we have to be careful which ones we choose. Here, this example here, this slide, which comes from the textbook manufacturer, by the way, is actually wrong. There should be an unexposed here, like NE rather than E. So here, the absolute risk in the exposed group is 6.6. The absolute risk in the not exposed group is 0.3. So the relative risk is 2, that divided by that. In this other example, the absolute risk in the exposed group is 0.2. The absolute risk in the not exposed group, that should be an N, is 0.1. And the relative risk is still 2. In both cases, there's a threefold reduction. The first case, threefold reduction in risk. Right? But the relative risk remains the same. This is a more profound scenario than this one. We went from 0.6 to 0.3 over here. The risk came down by 1/3. That's amazing. Here it came down by half. Not as amazing, but the relative risk is the same. So this is the relative measure. These are the absolute numbers. So we have to keep that in mind all the time. Okay? So it depends on which ones we're looking at. So with that in mind, we move on to the meat of today, which is correlation. This word that we use all the time in common day parlance, but has a specific meaning in statistics. Right? You've heard correlation is not causation and vice versa. Right? So in everyday parlance, a correlation, here's an example of, I looked at thousands of people and there's a strong correlation between those who are smart and those who agree with me. Right? So that's obviously a bias. Tough crowd. All right. So correlation is a bond, a connection, a relationship between variables. So one can say there's a correlation of being good looking and having dated me, right? That kind of thing. So that's a non-measurable kind of correlation. That's a common parlance conversational correlation. But today we're talking about strong quantitative correlations. And in general, we use correlations to explore relationships between continuous variables. Right? So, and I would count ordinal variables as continuous. And I'll show you some examples in a second. We tend to use a scatter plot to explore visually the relationship between two variables that may be correlated. Right? So here is examples of what a scatter plot is. But you're plotting one against the other, and you're looking for something that looks linear. The more of a straight line it is, the more likely it is a correlation. So we're going to find out there's a strong relationship between correlation and linear regression that we'll do later on. So the more closely related these things are, the more likely they have a linear relationship. Right? So here is an example, time and distance. If you have a vehicle that's moving with no acceleration, constant velocity, then the space that it moves every increment of time is constant, and so we get a straight line. If it was curved, that would mean there's an acceleration. So here there's a strong correlation between time and distance. Okay, so scatter plots like this allow us to look at the direction of the relationship and as well the strength or magnitude of the relationship. Directionality is this. Either it's this way or that way or this way. This way is a positive direction. This way it's a negative direction. Okay, and the strength of the relationship or the magnitude is how much it is clustered around this thing that looks like a straight line. You're never going to find, or rarely going to find, something that's a perfect straight line. You're going to find things that are kind of raggedly straight. That's what we're looking for here. So a line sloping from a lower left upper right is positive, and anything this way is negative. So this is a perfect linear relationship because for every change in x, I get exactly the same change in y. It's a straight line. A negative relationship runs that way, and this is a perfect negative relationship. So for every change in x, I get a negative change in y exactly at the same time. High school stuff. So the more tightly packed they are, the more strong the association or relationship is. Again, I'm very careful not to use the word causation. These are not causal relations necessarily. These are associations and relationships. So if they're loosely spaced, we say the relationship is weak. It's not zero, it's just weak. There's something happening here, If I were to show you this and ask you, if you had to plot a line there, what that line looked like, you'd probably say the line looks like this. So there's something happening there. It's just not clear. So we say that's a weak relationship. Now this, is there a line there somewhere? Probably not. Right? So here there's probably nothing going on. It's hard to say. How about this? What's happening here? Do you see a line here? Or 2 lines? Or 3 lines? Right? As you start to see that there's a lot of human value that comes into this. Is what we actually see here. We can model all kinds of things on a graph like this. So something called Fourier analysis. I can actually plot a curve through every single line, dot on this graph, if I make it complicated enough, but it's not really useful. So we're looking for something linear. This is what we call a curvilinear relationship. It kind of hops down like this, or we can model it as a straight line this way or a straight line this way. So this has no relationship. This has something resembling a relationship. What is it? This is actual data. This is actually Old Faithful, which is a geyser in Yellowstone National Park in the U.S. You ever watch Yogi Bear comics? I think that's where they are in Yellowstone, right? So there's a geyser there that erupts regularly. It's less regular than it used to be. It's interesting. So this is the waiting time between eruptions, and this is how long the eruptions last. So someone sat there and plotted like hundreds or scores of these eruptions, and they found there is a correlation between how long you wait for it to erupt and how long the eruption lasts. Look at that. It's actually clustered. We get the short duration intense eruption and the long duration less intense duration, long wait variety. So we learned something there about the geology of the geyser all of a sudden. It comes in 2 categories, the eruptions, but more or less there seems to be this standard relationship that says the longer I wait, the longer the eruption will be. And this was that. Hey, we're dealing with just 2 variables today, but it's possible to model a lot of variables in a correlational way, multivariable method. Don't worry about this. This is just what it looks like if you got multiple variables in the mix. Just let you know that there are more complicated things that await you in your future if you want to pursue this further. So this is a good public health example. Here we have the glasses of wine consumed, and this is, what is that? Heart disease cases. So 17 populations. Each of these dots represents a population, and it's saying the numbers of heart disease deaths in each population were plotted against the average number of glasses of wine consumed. So what does this tell us? What does that data tell you if it's an association between heart disease deaths and wine consumed? So what do you conclude about the relationship between wine and heart disease? There it is. So who's going to the wine and cheese at 4 o'clock? Right? Excellent. So consider that your invitation to lower your rates of heart disease. So this is the kind of data that was used in the 70s and 80s to start the whole Mediterranean diet craze, when people saying that there's association between drinking wine and lowering your risk of heart disease. It's actually associative data. It's not causal data, which is why it's a bit problematic. It's difficult to go from this to make the conclusion that wine is the cause of lesser heart disease. For that, you need further investigation. This is also what we call an ecological analysis. This is not relevant to this class, but just for your own personal benefit. An ecological analysis, each of these points is a population, not an individual. So just because the populations have lesser rates of heart disease, it doesn't mean someone in that population drank wine or died of heart disease. It's just that the population average was like that. So here's some of the nuances you'll come across as your health sciences degree progresses. Depending upon how we organize our data and the unit of analysis, an individual versus a population, we get different nuances. But this is, as pointed out, a negative relationship, somewhat linear, suggesting that there is a negative correlation between heart disease death and glasses of wine consumed. Okay. And this is, here it is. If you draw the line, it looks like that. And we'll do later on the semester how to compute where that line goes. Right. So another thing we look at is outliers. Here we have some data. I don't know what this data is, variable 1, variable 2. These guys are a pretty solid straight line, but that guy is out here. So right away we can look at who the outlier is. If we didn't look at the outlier and I asked the machine or the straight line computer or your eyes to find me the best possible straight line here, you'd probably say it's over here somewhere. And you get this artificially enhanced relationship between these two variables because that one guy is dragging everybody up. But in fact, this is the real relationship, and that guy just, what's he doing? Who knows? Okay, so right away, using the scatter plot, we can see who the outliers are. Not the only way. We talked about already box plots, whisker plots, and IQRs as methods of finding an outlier. This is another way to find an outlier. What's happening here? Is there a relationship here? Doesn't look like it to me. I don't see any straight line there. Okay, there's no relationship. We could force a straight line into this mix. It'll probably give you a straight line over here, which says nothing's happening. But not everything has a one-to-one linear relationship. So scatter plots show us relationship between two variables, a two-dimensional graph. They're useful to look at the strength of an association, and that's how much it is clustered around something that looks like a line. The shape, is it a line? Maybe it's not a line. Maybe it's that curvilinear thing you talked about. Okay. Later on in the semester, when we look at other kinds of correlation, we look at something called a monotonic relationship. It's not a line, but it's more or less when things go up. So look for that as well. Direction, is it going this way? Is it going that way? And are there outliers? So those are the four key things that a scatter plot gives us when we're looking at the relationship between two continuous variables. So here is a classic correlational thing. So what are we trying to compute here? We're trying to compute this thing called a correlation coefficient. There are many types of correlation coefficients. There are many ways of summarizing in one number the relationship between two continuous variables. And that one number tends to summarize the strength of the relationship, the direction of the relationship, and maybe the shape of the line or the curve that it purports to draw. We're going to do two correlation coefficients in this class. We're going to do something called the Pearson's correlation coefficient, or Pearson's R, and the Spearman's correlation coefficient, or Spearman's R. The R is not an R, it's actually a Greek letter rho, R-H-O. So I'll go back and forth, I'll call it an R or a rho. And we sometimes, they call it an R sub P or a P sub R. It varies. But today we're looking at Pearson's correlation coefficient, which is the most common one, and the one that has a close relationship with linear regression that we'll do later on this semester. Right, clear? Okay, so with Pearson's R, we can only use it with variables that are interval or ratio level. So those two really useful bottom levels of measurement, the two best continuous variables, not ordinal. Definitely not nominal. With Spearman's correlation coefficient, you'll see we can do ordinal. But today we're using just Pearson's. So these correlation coefficients range from -1 to 1. 0 tells us there's no relationship. There's nothing going on. 1 tells us it's a perfect relationship. It's a perfect straight line. So if it's -1, it means it's a perfect negative correlation. If it's +1, it's a perfect positive correlation. If it's 0, then there's nothing going on. So usually we get something in between 0 and 1, or 0 and -1. And obviously, the closer it is to either 1 or -1, the stronger the relationship is. Still with me? Excellent. So R of -0.75 is actually stronger than R of 0.5, even though -0.75 is less than 0.5, because it's the absolute value that matters. It's the closer to either -1 or 0.1. That's what determines strength. So there is a formula for it. We're not going to do the formula because we have computers. Why bother? Okay. So if I give you the formula and make you compute these things, what have I proven? I've proven you can use your calculators. Big deal. Okay. So this is what it looks like. Do you want to do this? No. Right? So you have a formula for it. It's there. SPSS will do it for you. Excel will do it for you. But I want you to know how to interpret it and what it means. So, happy? No. Yeah. People always ask, what was the formula? Well, there it is. Don't worry about it. So how do we interpret it? It's always between -1 and +1. Okay, the closer it is to either minus or +1, the closer to a perfect line it is. I said it already. And there are cutoffs. Sort of. Okay, so here's the hard part. Here's where the human element comes into it again. What does it mean? Where does a weak relationship become a moderate relationship, become a strong relationship? Here's one. If you go on the internet, you'll find literally scores of possible cutoffs. Here's one of them. If it's 0, then they don't vary. If it's between 0 and 1, then there's something going on. If it's 1, it's perfect. Right? That's pretty straightforward. Then there's this one. If it's 0.3 to 1, then it's small. If it's 0.5 to 0.3, then it's medium. See? Or I can use this one. From 0 to 0.19, it's slight. From 0.2 to 0.39, it's low, and so forth. Okay. Also, it applies to negative values. Same thing. Here's another one. If it's 0.1 to 0.7, it's strong, and so forth. So different statisticians like different ways of doing it, different cutoffs. So in general, you just report the number and let the reader make up their mind if it's strong enough. Personally, I like this one. Okay, that's an easy one to deal with. So that means that in this class, we use this. So if I ask you to interpret the quality of a correlation, we use this table. But I acknowledge the fact there are other ways of doing it. For the sake of being consistent for everyone, we use this table. So that means this is what you're going to study for your exams. Right? And true for the negative ones as well. All right. So here's some examples. Perfect positive relationship is one. E.g., a flat tax of $1 for every $5 earned. Some countries have that. So we have tax brackets, other people have flat taxes. So if you earn $10, you pay $2 in tax. $15, $3 in tax. If I plot the tax you pay against how much money you make, you get exactly a straight line. That's one. Here's a weak relationship. A nurse's degree of autonomy and job satisfaction. Right? So here we plot job satisfaction. Here we plot autonomy. So the more autonomy they have, sort of job satisfaction goes. So that's 0.35, very weak relationship. Nurse's degree of autonomy and height. If you're taller, do you have more autonomy? No, makes no relationship whatsoever. That's a 0 relationship. Here is diabetic knowledge and a person's age. So the older you are, do you have more knowledge of diabetes? It is a slight relationship, not a lot. It's actually negative. The older you get, the less knowledge you have, because old people aren't as well educated in these things as we are. And levels of depression and life satisfaction. So here, if we plot satisfaction with your life and increasing depression over here, the more depressed you are, the less satisfied you are in your life. So it's negative and quite strong. Okay? So here I've interpreted these correlations. 0.2 is low and quite small. Right? Here, 0.7 is high correlation. So that's how that works. So what are the things that affect correlation? The range will affect correlation. So let's say I'm trying to determine if there's a correlation between how many rooms there are in your house and how much money you make. So you can make anything from $0 to $1 million. It's a big range. How many rooms can you have in your house? You can have 1 room or probably 5 or 6 rooms. You know, there's a hard limit cutoff how many rooms you can have in your house. So the range of the number of rooms is actually small. The range of your income is actually kind of large. And that inability to have range will actually affect the correlation. It'll constrain it to a strong degree. So we prefer to be able to compute correlations for things of similar ranges. At least for Pearson's correlation. For other kinds of correlation, they're more forgiving for incomparable ranges. So here is the correlation between the age of someone who lives in Canada and how many children you have. So the older you are, the more children you tend to have. But you kind of stop in your 40s having kids. So in your 70s, you're not gaining more kids. So you can live to be 100, but you probably max out at 4 or 5 kids. So that correlation looks kind of weird because the ranges are stunted. Here's some things that really correlate well. Height and age. So the older you get, the taller you get until you hit your 20s. Then you kind of stop growing. So it probably goes, then, right? Education and income. So the more educated you are, the more money you make. Well, not always, not anymore. There was a time that was true. But again, there's a cutoff for there too. So, but education has limited range. You get how many degrees you have? Well, probably max 4 or 5. And how much income? Well, unlimited. Height and weight. So the taller you are, the more you weigh. And that's pretty consistent. That's like that. And so forth. Right. Now, does that mean that height caused weight? Maybe. A little bit. Not entirely. Does that mean education caused income? A little bit. Maybe. Does height cause age? No. Does age cause height? Maybe a little bit. So it doesn't tell us a lot about causation. It hints at it. It gives some information. That's about it. So here's some examples again. Here is a perfect negative correlation. This is very close to very good positive correlation. This is a crappy negative correlation. This is zero correlation. So here is a famous case of correlation. Here we have a number of shark attacks, and here we have ice cream sales of a particular New England town. What we find is, as shark attacks increase, so do ice cream sales, almost linearly. What do you conclude from this? This is real data, by the way. Sorry? It's nice outside. It's nice outside. Exactly. It's nice outside. You probably read about this in the book, isn't it? So what we're looking at here is actually good weather. So if it's nice outside, you're more likely to go swimming, and the sharks are more likely to attack you, and you're more likely to buy ice cream. So there's another factor at work here. It's easy to mistake strong correlations for causal relationships. Hence that statement, correlation is not causation. However, it is one factor in establishing a likely causal relationship. I don't know for sure that smoking causes cancer because I can't really do the experiments. I can't make you smoke for 20 years and see if you get cancer. Instead, I have a series of other factors I look at, like, is it strongly correlated? Does smoking come before cancer typically? Yes. Is there biological plausibility? Yes. Does it work in animal subjects? Yes, etc., etc., etc. So we bring to bear a host of tools to determine likely causation. Correlation is just one of them. Here's a, I used to think correlation implied causation. Then I took a stats class. No, I don't. Sounds like the class helped. Well, maybe. Is there a correlation between studying stats and understanding? Maybe there is. I don't know. So correlation does not imply causation, but we have this other thing we can do with the correlation coefficient, and that's we can square it. We've computed R. If you take R squared, it gives us, or rho squared, it gives us a very special measurement that determines the proportion of the variance in one variable that is explained by the presence of the other variable. So think of it this way. If your rho is 1 and you square that, you get 1, 100%. So in other words, 100% of the variation in this variable is explained by the presence of this variable. If your rho is really high, like 0.9, you square that, you get 0.81. So 81%, that's pretty high. 81% of the variation in this variable is explained by this variable. The lower you get, the less R square becomes, and the less of the proportion that this variable explains of the other variable. So it's a useful kind of trick that we do. And very often we look at the square more than we look at the rho to determine the true extent to which this relationship is meaningful. So case here, the rho between height and weight is 0.6. You square that, you get 36%. So we say 36% of the variation is weight is accounted for or explained by the differences in height. So what's the remaining 64% caused by? Well, that's other things. That's like calorie intake, exercise, genetics, metabolic factors, and so forth. Right? Obviously, it's not a foolproof method, but it's a great hand-waving methodology that we use to determine how much of one thing is probably, I'm going to use that word caused by, but explained by the other variable. Cool. So when you run correlations, if you have several variables in your data set, like let's say you've got, in your data, you've got age, salary, height, I don't know what else, weight, and you want to see, hey, what's correlated with what? And you go to SPSS or Excel, and you push all of those variables into the soup and say, give me the correlations. You get a correlation matrix, which gives you everything correlated with everything, and it looks like this. Right? So you've got all the variables listed here and all the variables listed here, and all you care about is one half of it, because down the diagonal you get the correlation of a variable with itself, which is always going to be 1, and here it's A to B, 0.82, here it's A to C, 0.23, etc. SPSS will give you this side as well, which is exactly the mirror opposite. So if you run a correlation, you'll get a matrix. It's fairly obvious what it is, but sometimes you get confused. What am I looking at here? You're looking at this correlated with that is that. This correlated with that is that. Right? Cool. So how do you do it in SPSS? You go to the Analyze button, you click on Descriptives and crosstabs, you select the variables, and you select the statistics here, and they'll probably give you the totals, and where is it? Risk gives you relative risk, which isn't great. And here you can get the other things. You get Pearson's correlation coefficient. Notice there are three of them here. There's Pearson, Kendall's tau, and Spearman. Today we talked about Pearson. Later on we're going to talk about Spearman. We will not talk about Kendall's tau, but know that it's there. All right. I think that's all. That's your homework. Straightforward stuff. Look at that. Half an hour. You're free in half an hour. Is that wonderful? Okay, we'll see you at 4 o'clock at the Wine and Cheese. I'll be there, yeah, totally.